somebody asked me about a tall residential building, the question of how many stairs do you need for a tall residential building, and I was to answer none. What would you think? Clearly that question is loaded, because if I gave you the freedom of design and allowed you to implement a safe solution that doesn't require any stairs, we will have the capacity to deliver that. Nevertheless, the way in which we think is we always think of fire as a constraint. So effectively, the stair is already a constraint that is embedded in the design process. So you are, by definition, required to have 1, 2, or as many stairs as whatever the code requires. And therefore, that states the premise under which you are designing. Without recognizing that the moment that you accept that you have to get people out of the building, you already accepted failure. While in reality, if you don't accept that premise and you insist that actually you're going to design the building without any stairs, then you cannot tolerate failure, and therefore your design will probably be a lot more robust. And you will put considerations within the design process that effectively enables you to design a building without a stair. So we need to start thinking in a slightly different way, and I think this is sort of the subject of this talk. And many times people say, you've been repeating this for the last 15 years, and yes, I mean, there's slides in this talk that actually are 15 years old. And I think that, that the reason why I keep repeating it is because people don't seem to listen. And it is not because I am right or I am wrong. I think it is about a dialogue that we have not been able to establish. So I think that I'm going to fly through a number of different points just to illustrate how we are not thinking in terms in which we can actually address problems such as robustness, resilience, and optimization. Now, why are we not addressing these problems? The reason why we're not addressing these problems, because at the core of being able to optimize, at the core of being able to establish robustness or to establish resilience is performance. We have to be able to quantify performance in an explicit way. Once we've been able to quantify performance in an explicit way, we can add a safety factor. We can add mechanisms of robustness. We can assess how fast we can recover, and we can talk about resilience. Or we can do a true cost-benefit analysis and optimize a system in a way that is most appropriate. So let's start with definitions. So people have all sorts of definitions for these terms, so I'll just make my own. Okay, and there you have a case where all the things that I've been talking about didn't work. That's the Tay bridge, and effectively what you have is a failure. Okay, now when we're talking about a situation like this, there was an attempt to optimize. As you can see, very, very slender structural elements, and the objective was to minimize resources while maintaining an adequate design. Clearly, that was not the case in this particular scenario. Robustness is the capacity of a system to positively respond to solicitations greater than what they were designed for. In other words, I design for a certain set of parameters, but sometimes those parameters get exceeded. And the concept of robustness is how well can I cope, with solicitations that exceed the design parameters. When it comes to resilience, it's the capacity of the system to recover. So effectively, we are pushing the bounds to the point where we are inducing certain forms of failure, and we need to be able to understand how rapidly we can recover. A resilient system is a system that recovers very rapidly. A non-resilient system is a system that takes a long time to recover. So finally, a disaster is an event or an outcome of an unforeseen negative magnitude. So effectively, I'm going to be using this terminology, but I'm going to define it in those terms. I know that there's many other definitions, and people will argue, many different approaches to those terms, but I'm going to be using them in those terms. So a disaster is a case that we didn't plan for. In other words, we expected a certain response, and we got something that was much worse than that. Okay? So The alternative to all that, when we stop talking about optimization, we stop talking about robustness or resilience, because there's no point. It's a case where I completely over-dimension. So as I'm sure you're all familiar with that photograph, this was the response to the Tay Bridge disaster, so that's the 4th rail bridge. And you can see that this system was literally, not only very nicely designed, but also there was an element of over-design that was embedded into the system. In those cases, basically none of these things, mean anything. Okay? Because effectively I'm just completely over-dimensioning, and I'm over-dimensioning to try to avoid a problem that I can actually not understand. So it is clearly not a matter of optimization, resilience, or robustness, and I'm trying to just simply prevent the disaster. So, what is optimized design? So, when we're talking about optimized design, we need to take into account all these 3 aspects of it. And many people have seen diagrams like this, like Candela's diagram of this very thin concrete shells. And in that case, basically, it is a truly optimized design for structural purposes. So, for an optimized design, resilience and robustness can only be achieved by precise understanding of the system performance. So, if you don't understand, the mathematics of the structural system, in this particular case, you will never be able to actually design a thin shell that works the way Candela designed that thin shell to work. Okay, so we need to be able to have a true understanding of the performance of the system, to be able to achieve the objective. So at the core to me is that if you can actually explicitly quantify performance, then you can do optimization, you can analyze robustness, and you can analyze resilience. And the question is, can we actually do that for fire? So when we're looking into optimization, we are not today doing that in the case of fire. What we do in the case of optimization, we're going to basically take a function, and that function has a set of variables, n different variables, and it gives me a performance metric. Okay? So if I'm going to optimize, what I'm going to do is I'm going to create some sort of summation of the derivatives of all those functions, and I'm going to either maximize or minimize that sum. Okay? So I put all my variables, I look at all the derivatives, and when the derivative approaches 0, then I'm reaching either a maximum or a minimum. Okay? And I fix all that through some sort of algorithm that allows me to pile up different variables into that function. Okay? But the key to this is that that sum that I'm working on is from I equals 1 to I equals n. In other words, to be able to optimize the system, I need to be able to optimize simultaneously all the variables, because all the variables represent trade-offs. So effectively, if I'm bringing one up, the other one has to come down in such a way that at the end I arrive to the optimal function that I need to work with. The problem is that when it is in regards to fire, what we're doing is effectively we are optimizing for n minus 1. And once we optimize for n minus 1, and then we slap the fire, the outcome is never the optimal. Okay? In other words, this is a mistake. We cannot optimize in those terms, because effectively you are optimizing all the variables, and then you're adding on the fire as the final variable of the problem. And that is very problematic. Now you can see that in the current approach, because obviously the current approach is that of fire resistance, and it was a very old process that came as a result of the obvious weaknesses of some construction methods. As you can see here, the steel beams hanging on top of the timber beam. Okay? So we had a very simple problem that we needed to solve, and we tried to fix it by creating the concept of fire resistance. And that concept of fire resistance led to this particular curve, and that particular curve was devised with tests that looked like this. Okay, so this is the 1920s, and this is what we were doing. So we were trying to achieve a worst case scenario, not an optimal condition or the understanding of the problem, just a worst case scenario. And basically we created an envelope to that worst case scenario, and then we created a failure criteria that effectively was related to total fuel consumption that gave me the required fire ratings. That doesn't mean that I understood the problem. That doesn't mean I understood structural behavior. All that means is I created an artificial scenario that made me comfortable that I was on the conservative side. Okay?
Then there were a lot of arguments that were made about restraint in such a way that you could test a single element and then project that to global behavior. Okay? God knows if that could have ever worked. The problem is that we've carried those arguments, enabling us to work with a single element testing and extrapolating that to full structural behavior. Okay? So we did all that, then we created the standard file, we created a test, the furnace reproduced that particular worst case scenario, and we rely on a very simplistic failure criteria, for example, in the case of steel, arriving to a certain percentage of its mechanical properties. So we determine after we lose a certain percentage, then we go here, and then all of a sudden we can say, well, if I'm heating the structural element, and I can basically find that critical temperature, I can get my fire resistance. So if you think about it, what's physical about this? Physical about this is not the fire. The fire is a mathematical envelope to an event that is actually a compilation of events, so it's just an envelope. The requirement of fire resistance is based on total fuel consumption. Now, total fuel consumption in many ways depends on so many variables that whatever way it was defined, it was probably not necessarily a physically based definition, it was just purely an arbitrary test. The failure criteria utilizes one physical parameter, but it ignores many other parameters like thermal expansion, for example. And then all of a sudden, we've eliminated all the physics of the structural behavior. So effectively, this is not a physical problem. It is just purely a concoction that we have created to try to describe in a conservative way a form of behavior that we want to avoid. Okay, that's really all it is. Now, can this allow me to do optimization? Not at all, because the problem is that effectively I don't know what problem I'm modeling here. All I am doing is creating a concoction that then I can put into regulation that effectively eliminates 99% of the physics of the problem. So, all these concepts of optimization, resilience, and robustness clearly cannot be used in the context of fire resistance. It is not possible. It's the optimization of n-1 variables plus fire, and it is adding fire in a completely non-physical way. So the first step is to accept that the way in which we do it has nothing to do with this terminology. This has absolutely nothing to do with optimizing with resilience or with robustness. It is purely a concoction that is regulatory, that effectively allows us to design under an umbrella of comfort that we are within the conservative bounds. So, very, very simple. So this is something that a former student of mine, Alan Jausi, presents quite regularly, which is the most simplistic form of optimization, money. So if you take the cost of steel, it increases linearly with weight. If you take the cost of fireproofing, it decreases as the steel member becomes bigger. Okay? So effectively, the cost of a steel plus fireproofing is the summation of those two curves. So effectively, you get that curve. Optimization means that you are here. Is that okay? That is the minimum cost that you have for the system. So when you have fire resistance requirements, you're going to introduce them after the design process. So the structural engineer is going to try to optimize for the minimum amount of steel. So they're going to go as far as possible as they can in here. And therefore, then they're going to slap the fireproofing and they're going to end up here. Okay? Well, in reality, if the two things were done together, you would not be in a situation where you have not optimized the system, but you will be in a situation where you actually are attaining the minimum cost. So it's as simple as that. Even in the most simplistic of analysis, you realize that the process that we're following is not leading to optimization. Okay? So in a similar manner, we have the fire resistance framework that depends on the existence of a compartment. The whole worst case scenario was defined about that. Now, if you look at this, maybe this was valid all the way till some time in the 1960s, but clearly beyond that, the whole concept of the compartment is gone. So the physics now doesn't even resemble reality. So can I actually talk about robustness, resilience, or optimization, where now I have a problem that has nothing to do with the problem that I originally set myself up to solve? The consequences, you have different fire regimes, you have loss of load redistribution capacity when you have, for example, a traveling fire that is moving around. You have untested structural behavior, all sorts of different things that appear, at that point. Now, World Trade Center 7 is a perfect example of that, and it shows, that you can have a fire that has absolutely nothing to do, with the existing framework. So, how do we do true optimization? Basically, we need to establish structural performance. We know how to do that. You've all been working for ages in this matter, and there's a lot of work that has been done, and structures have been understood to a great extent. Nevertheless, we seem to believe that somehow the problem has only one side. So if I look at true performance assessment, the first thing that I need to do is to be able to understand the fire dynamics. That fire dynamics is going to give me a heat flux to the structure. That heat flux is going to be embedded into a heat transfer model, and that is going to lead to a structural analysis. Right now, all this is a fire resistance test, okay? But it's not the reality of a compartment. So, nevertheless, when Asif developed this many years ago, he put a very simple expression that effectively defined, the displacements as a function of fundamentally two parameters, the temperature and the temperature gradient. So without the temperature gradient, you don't get the value of phi, and you cannot get the behavior of the structure. So it's not only about the energy that you're putting in the structure, but it's about the rate at which you put it in. So if you don't have the temperature gradient, then you don't have structural behavior. Now, it's very, very simple. So it's essential to be able to have the temperature gradients. Now, the temperature gradients depend on the net heat flux, and therefore depend on the fire. Does the furnace deliver the temperature gradients that I need? Well, clearly not, because if you look at furnace testing, and I change different materials, here is the temperature versus time curve of the furnace, and every material corresponds to that particular evolution of temperature as a function of time. And as you can see, depending on what I'm testing, I get a different temperature gradient. And if I'm testing timber, I get negative temperature gradients because the timber is delivering heat to the furnace and not the furnace delivering heat to the timber. So effectively, what we're doing has nothing to do with reality. And while structurally, we have identified that the temperature gradient is an absolutely critical parameter, we rely on a testing procedure that delivers different temperature gradients for different materials that you're testing. So in principle, you can see where the problems go. But nevertheless, despite the fact that we know that the heat flux is the eigenvalue that I need to solve, I still stick to a testing protocol that effectively does not deliver the fundamental parameter that defines structural behavior. So, do we have tests that give me those gradients? We do, but we don't use them. We still go back to the framework. So, we have heat fluxes. We know they're a strong function of the fuel, the ventilation of the compartment. We know many, many, many things about it, but we don't manage to marry these two professions. Now, we know it matters. If you take a beam, just a simple I-beam, and you look at deflections, you can see that a very simple analysis is conservative. And effectively, this was done by Darlene Rini many, many, many years ago, and effectively showed that if it's a simple beam, the simple analysis is conservative. Nevertheless, if you do a cellular beam, and now you're heating the web much faster than you heat the flanges, then all of a sudden what seemed to be conservative is no longer conservative. So as you can see, it does matter. You can land from a very conservative approach if you're using the simplistic analysis to a very non-conservative approach if you're not calculating your heat fluxes correctly. So effectively, it does matter. And these are the consequences. Every time we use the wrong science and we shift the problem, we land in something that we didn't expect, the disaster. So this is a perfect example. When we used to have concrete slabs between floors, we had a very simple approach towards eliminating vertical flame spread. Okay? A big concrete slab serves as protection. There is no motion. Structural components are minimized. This became a very simple, robust, conservative approach. Okay? The moment that we did this and we changed this, and now you have a completely different problem, then all of a sudden you went from this to this. Not only we went from this to this, but
The moment that we change the problem and we put a very complex connecting system, where now you're talking about trying to stop the fire from penetrating this gap, where you have a fire and you have relative motions, we turn a problem that was a very simple barrier problem into a problem of relative displacements. Now people are going to tell me, oh, but it's all about the flammable cladding. That's nonsense. We accepted flammable cladding in those materials, but we encapsulated. The concept that we created was the concept of encapsulation. And encapsulation of combustible materials fails because of relative displacements. Effectively, you get pieces moving from one side to the other one until the system breaks, you lose your encapsulation, all of a sudden you've exposed the combustible materials, and now you have a problem. So it is not a problem of flammability, it is a problem of structural mechanics. And all of a sudden we have not been able to interpret that in an appropriate way. So the consequences, we know them, and I don't need to really dwell too much on this. These fires keep happening and will keep happening, and we have absolutely no idea what to do about it. Okay? So, in a similar manner, we want very tall timber buildings. And the question is, can we predict performance? Can we use the tools that we have to predict the performance of tall timber buildings? Are we answering the right questions? Are we using the right physics? Now, the bottom line is, are we capable of delivering optimized, robust, and resilient solutions for timber? Now, in the face of that, again, we have all these examples, and they keep happening, and we don't know what to do about it. Nevertheless, we still believe that we can do it, and we can do it within the context of the same framework. So, when it comes to design, how can we truly optimize the structure if we're targeting the wrong loads? This is a real problem that we have. How can we establish if a structure is robust or resilient if we cannot quantify performance? So until we change our mindset and we start thinking in a completely different way, and we move away from these existing paradigms, we're not going to be able to talk in the same terms as other professionals talk in this field. So basically, it's a problem of competency. We've rendered ourselves incompetent by complexity, and we are standing within our framework thinking that it still works, when in reality it actually doesn't. So in summary, optimizations, resilience, and robustness, and disaster prevention require true quantification of performance. True performance requires understanding of structural behavior in fire in as much as it requires understanding fires within structures, and it's in the marriage of these two fields that you actually get proper quantification of performance. Thermal load is a parameter affecting the performance, therefore the performance cannot be established if the thermal load is the outcome of a test. So in other words, we need to be able to vary that parameter and work with that parameter as opposed to getting the parameter out of the test, which is not necessarily relevant or comparable to anything that is realistic. So without true performance assessment, there is no optimization, resilience, or robustness, and we have to be accepting of that premise. Unless we quantify performance, we will not be able to use that terminology when it comes to fire. So the science has to be there, but it has to be the right science. So in other words, we have to be addressing the right problem. There is no point in us chasing one problem when in reality we have a different problem. So finally, do we need to rethink competence? And I think we do. And it's not necessarily in the specific physical knowledge or chemical knowledge or materials knowledge that we have. It is more competency in the way in which we think about design. We need to start thinking in a different way to be able to use the tools that we have in an appropriate manner. Thank you very much.
So we have some time for questions.